In this week's lab, we're going to use the UV visible spectrum for iodine in order to try to extract functional or structural parameters about iodine from the numbers in that spectrum using a lot of complicated theory in order to make the connection between the spectrum and the structure of iodine. So this week I'm going to talk about the theory behind everything, and next week we'll talk about the data analysis. These notes will go up on the website, on the Learn site, of course, in the meantime, so you can go ahead and look at the data analysis section down below, even though I won't talk about that today. So if you want to get a head start on the computations and stuff, that will be fine. Of course, like last week and like next week, which will be the last of our labs, this week's lab is entirely sort of a dry lab. We'll just be giving you the iodine spectrum rather than taking it ourselves. In truth, even without the coronavirus problems, the experimental part of this lab is pretty trivial. It amounts to taking a cuvette full of iodine and putting it in a spectrometer, heating it up to 65 degrees, and then taking the spectrum. So just getting the spectrum is a little, you don't get the experience of actually taking the spectrum, I guess, but there's not too much experience in that anyway. So, all right, so let's talk at first about the basic ideas behind a spectrum. And to do that, we have to begin by talking about what kinds of degrees of freedom there are in a small molecule. So this is I2, it's a diatomic. It's a homonuclear diatomic, so that means both ends of the diatomic are the same atom. A heteronuclear diatomic would be something like HCl, where, actually let me write it the other way since the little atom should be the H, where the two ends of the molecule are different atoms. And one important difference between a heteronuclear and homonuclear diatomic like this is that the heteronuclear diatomic can have a dipole moment, whereas a homonuclear diatomic really can't, because both atoms are the same. There can't be any charge difference between the two just by symmetry. And we'll see that that has some effect on our experiment and our data later on. But for the moment, let's just talk about the degrees of freedom in a general diatomic. There's a center of mass between the two atoms. In the case of I2, it's right dead center. In other molecules, it's not necessarily. In heteronuclear diatomics, it may be off-center. It generally will be off-center. And the position of that center of mass gives 3 coordinates, or requires 3 coordinates to specify. So that's 3 degrees of freedom for the molecule. And then there are rotations around the center of mass. And in general, for a complicated molecule, that's 3 more degrees of freedom. It takes 3 angles, this one, and this one, to specify what the orientation of the molecule is around the center of mass. But for a homonuclear diatomic like this, or any cylindrically symmetrical molecule, whether it be homonuclear or not, in fact, for any diatomic, and also for things like CO2, molecules like CO2 that are linear and therefore cylindrically symmetric, then this last coordinate here, this last angle here, doesn't count because there's nothing to spin around that axis. And in fact, the only things that can spin around the axis are the electrons, and that gets counted as part of the electronic wave function, not the rotational parts of the wave function. So we'll come back to that in a minute, but there's only 2 angles for our molecule I2, that means. So 3 degrees of freedom here, 2 more here. And then there are internal shape changes in the molecule. That amounts to, as long as the changes aren't very big, as long as the stretching and deformation of the molecule is pretty small, we can describe those changes as vibrations, as a set of normal modes. In the case of an I2 molecule, there's just one normal mode, or one vibration, one stretching degree of freedom. All right, those degrees of freedom, each of them has an energy associated with it. There's a kinetic energy associated with the center of mass. There's rotational kinetic energy associated with the rotations. There's kinetic energy and potential energy associated with vibrations. And roughly, approximately, the overall Hamiltonian can be written as a sum. Now, this isn't exact, it's an approximation, but roughly, and to a good approximation, in fact, usually, the overall Hamiltonian can be written as a sum of contributions to the energy from each of the degrees of freedom. There are 4. I haven't mentioned only in passing have I mentioned the electronic degrees of freedom, but that's in there too. So there's the translations, the rotations, and the vibrations, and then finally also, yes, the electronic degrees of freedom. And they're at least approximately independent. You can see what the Hamiltonians are here. I've written them out. So kinetic energy P squared over 2m, rotational energy L squared over 2I. I is the moment of inertia. That's just the potential energy, actually, for the vibration. There's also a kinetic energy term that I didn't put here for the vibrations. And then the electronic energy is, I didn't write anything because it's very complicated, and I think everybody has probably, well, people have seen a little bit at least of what that looks like, probably in PChem in 311. Anyway, the fact that these degrees of freedom are roughly, at least, independent of each other means that the wave function for the overall wave function for the molecule can be written as a product of independent wave functions, and each of these is the solution to a Schrodinger equation for a different kind of problem. The translational one is the particle in a box. The rotational one is the rigid rotor problem. The vibrational one is the harmonic oscillator, and the electronic one is the thing that gets addressed or dealt with in Hartree-Fock theory, for example, and other kinds of theories like that. And the energies, the energy levels for the molecule can then also be written as a sum, roughly again, approximately as a sum of translational terms, rotational terms, vibrational terms, and electronic terms. That means that you can write out the energies, or represent or draw a picture that represents the energies. It looks something like this. First of all, these curves here represent the potential energy of the atoms as they're stretched to the breaking point when you're out here. So this is R along this direction. So as we're moving in this direction, we're stretching the molecule, the I2 molecule. And when you're way out here at very large R, you've broken the bond, right? That's what it means to be, when you're down here in the bottom of the well, that means you've got a bond. You're at lower energy than you would be if the atoms were separated. Here, the atoms are separated so that you don't have a bond anymore. And over here, if you start trying to push the atoms too close to each other, then they start repelling, or basically you're trying to force 2 atoms on top of each other, and so the energy starts rising again. So this represents the potential energy to stretch the molecule when it's in its electronic ground state, and this one represents the same thing, but for the molecule when it's in its first electronic excited state. So this is called the excited state manifold, and this is called the ground state manifold. But then on top of these manifolds that represent, the potential energy of stretching the bond, there's a series of levels due to vibrations. So these guys are the vibrational energy levels. These are the vibrational levels for the ground state, electronic state. These are the vibrational levels first excited electronic state, and they aren't the same. I've drawn them roughly the same here, but the spacings between these levels are not the same in the two electronic states. And then on top of those vibrational states, there's a bunch of little rotational states that come from the rotational part of the overall Hamiltonian as well. We won't deal with, we'll look at the electronic states, the electronic manifolds in this experiment, and we'll look at the vibrational manifolds as well, but our spectrometer doesn't have enough resolution to resolve these vibrational states. It takes a very high resolution spectrometer to see those, and probably you have to go to low temperature too. So we will see basically that these rotational levels, they're there and they have an effect, but they basically smear out and make the bands look a little wider and fatter than they otherwise would be. We're basically going to average over all these rotational transitions. All right, so that's what the energy levels for a diatomic molecule look like. And let's see, you can make transitions between these things, right? So if I send in light of the right energy, you can get a transition between two rotational levels. That basically means that you will make the molecule spin faster by basically putting in some electromagnetic energy from outside. Or you can get a transition between two vibrational levels, either within the ground state manifold or within the excited state manifold. Or you can get a transition between two states in different electronic manifolds. And these different types of transitions correspond to different energies and therefore different parts of the electromagnetic spectrum. So this is mostly microwave, when you're getting transitions directly between rotational states. This is infrared, when you're getting transitions between vibrational states. And this is the UV or visible part of the spectrum, where you're getting transitions between different electronic state manifolds. We're going to be using the UV-vis part of the spectrum, and therefore we're going to be looking at transitions that always involve a jump between two different manifolds, but may also involve jumps between different vibrational levels. You'll notice that the green arrow there starts from the ground state vibrational level, but ends up in an excited state vibrational level on the electronic manifold. And so we'll be looking at a series of transitions that are like this, where you start from the same ground state vibrational level, but end up in various different possible excited state vibrational states. All right. So why not use IR or microwave radiation instead of using UV-vis? Well, the UV-vis has some advantages in its own right, but there's a really good reason why we don't use microwave or IR spectroscopy for this experiment, and that is that the I2 molecule can't have a dipole moment. That's what I mentioned way up above. And as we'll see down below in the next page, that means that there aren't any visible transitions with microwave or IR radiation. You can only see the transitions that we're after by using UV-vis radiation. So let's see why. Let's suppose you have a molecule with a dipole, like HCl, and now you send in an oscillating electromagnetic field. That's what a light photon is. Well, you can see how if the frequency of oscillation of this electromagnetic field acts on the dipole moment of this HCl molecule, then and if the natural vibration frequency of the HCl matches the frequency of the electromagnetic radiation, then every time you get a compression, the light energy will fortify that, will push in the same direction, and then when the molecule turns around and starts expanding, the light energy will also turn around and push in the same direction. So it's like pushing on a swing, right? If you push with the right frequency, the swing goes higher and higher, and that's what happens also when the frequency of the light matches the frequency of vibration for an HCl. But you have to have a dipole moment for that to work. There's nothing to push on if there isn't any charge difference between the two atoms. So what the electromagnetic field is working on is pushing on one direction, the minus sign, in the opposite direction on the plus sign. If both atoms are the same, there's no net charge, and you just don't get any revving up due to the incoming light. You just don't get the kinds of transitions. You don't induce a transition without that dipole moment. Same thing for the rotations here. If you start rotating with a certain frequency, you can see that by putting in oscillating light with the right frequency, you can rev it up just like pushing a swing again, or just like the case for the vibrations. And so it's the same idea, but again, you have to have a dipole moment to do that. If you don't have a dipole, then it doesn't work. So we have an excellent reason to use UV vis spectroscopy in this case. It's the only one that will work with a homonuclear diatomic like I2. All right, so what will happen then? What kind of a spectrum will we see? Well, what you see in an electromagnetic spectrum are the energy differences between the levels, right? So if I start with a certain vibrational level here and go to a different vibrational level up on the next electronic level, and then maybe also a different rotational level within each vibrational level, then that corresponds to a certain energy, a certain wavelength, a certain frequency, and that will show up as a peak on the spectrum. If you've got a lot of little fine structure like this on top of it, then you can get transitions within any one of these little tiny closely spaced levels, and that means you'll get a whole cluster of peaks, all closely spaced, all at very nearly the same wavelength. But then when you jump and start looking at the transitions up to this level, we'll get another cluster of peaks, but at a higher energy, and likewise for the next cluster of peaks and so on. And so you'll get a spectrum that looks something like this for all the transitions that started from the same vibrational state in the ground state manifold. In other words, everything that started here corresponds to all these black peaks. But now suppose you start from here, from the next level up, and you go to all the possible transitions up here on the excited state manifold. Then you would get a different set of peaks, and that could correspond, or I mean in my rough diagram here, that would correspond to all these blue little clusters of peaks. And so you get a spectrum that's got clusters of peaks that can be put together or understood as consisting of manifolds or groups of transitions. So the black set and the blue set, they kind of overlap with each other, but they correspond to different types of transitions. So what we're going to be doing is trying to understand. We're going to get a spectrum that's going to look something like this, not quite as complicated as this. Actually, let me say something about that. Because we can't see the rotational fine structure on here, we're going to get something that looks more like this. The rotational fine structure gets averaged or smoothed out, and you get a spectrum that looks like this. But okay, it's the same idea, and what we're going to get from that by looking at the spacings and positions and gaps between all these is we're looking at the different gaps between the different levels. We're going to basically be able to reconstruct what all the levels are like in our I2 molecule. And we're going to use that to extract information about the parameters that control these levels in a model for the I2 molecule. So let's now talk about that model. There's two possible models you can consider. We're not going to talk about the we're not going to talk about the rotations anymore. We're only going to talk about the vibrations, and we're only going to talk about the first two first two levels, electronic levels, the ground state and the first excited state, and we're just going to take those as givens. We're not going to make a model for those. There's really only one parameter that describes those. That's the energy gap between them. And we'll see, we'll get that in the end. But there's not too much to say about that. There's no Hamiltonian or model for that. So it's all going to boil down to the vibrational model. And there's two possible vibrational models. One is the straightforward harmonic oscillator model, for which the energy levels are all equally spaced. So V here is a quantum number that goes from 0 to infinity. And the spacing between the levels for the harmonic oscillator is constant from one gap to the next, and it's equal to this fundamental frequency, or this fundamental energy gap, h times the fundamental frequency, nu sub e. Now, spectroscopists, there's a little bit of a complication here. Spectroscopists love wave numbers. I don't know why. I'm not a spectroscopist myself, but they do. And so they divide everything by hc. I guess they find that convenient. It's kind of confusing as far as I'm concerned, but anyway, they do. So, and I can't, change the spectroscopy world. So almost everything we're going to be talking about, all the energies are going to be divided by hc. And so we're going to talk, energy divided by hc is still proportional to energy, right? So it still can be thought of in a sense, except for units, it basically is energy. And if you divide this side of the equation by hc, you get something called omega usually. Well, that's what the write-ups call it here anyway, and that's a circular frequency. But anyway, it's proportional to energy. That's all what really matters. And then over on this side, you get a frequency divided by the speed of light, c. And that's a wave number. It's usually written this way with a little bar over it. At least that's the way I've always seen it. But in this write-up, they use this omega sub e notation to indicate this same number. So all these omegas are wave number quantities, and I'll talk more about what a wave number is for those of you who might find that useful next week. I don't want to get distracted with that detail right now, but it's the important thing is that it's proportional to energy. So this is basically an energy gap size, and this is an energy level value, and so on. A little bit more just to remind everybody, the fundamental frequency for a harmonic oscillator is 1 over 2 pi times the force constant for the bond that's holding the two atoms together, divided by the reduced mass for the molecule. And the reduced mass is this quantity. It's the mass of one atom times the mass of the other divided by the sum of the two masses. And, well, I think I'll just leave it at that, presumably. Presumably everybody's seen that already. All right, so the harmonic oscillator is good if the potential that's holding your two atoms together looks like this. And it does look like that if the vibrations are small enough. But in some of the cases, in fact, we'll see it in the spectrum, our vibrations are going to get big enough so that the potential energies between the two atoms doesn't look like this. It's not a harmonic potential. It looks more like this. It looks like, yeah, the bonding potential between two atoms. Of course, that's what the true matter is. If you're down here at low energy, so you haven't moved very far from the ideal bond length for the molecule, that is, if the vibrations are pretty small, then it is approximately harmonic. That's what this dotted line is. But as soon as you start getting up to higher vibrational levels, of course, it's not harmonic anymore. And so we introduce a better model for the bonding between the two atoms, and that's called the Morse potential. And the Morse potential is given by this function, which looks a lot like this. I won't say too much more about it except to point out that the Morse potential has 3 parameters that describe it, and we're going to be trying to get these parameters, so it's important to pay attention to what those parameters are. One of them is this value dE. That's the depth of the Morse potential. That's basically the bonding energy. It's something very closely related to the bonding energy for the I2 molecule. That's obviously important. Another parameter is this quantity beta. That's the sharpness, and it's closely related to the force constant for the molecule. We'll see that. The third quantity is the position or the bond length, the equilibrium bond length for the molecule. And we won't be able to get that. The spectroscopy doesn't tell us that, but we can get these other two. All right. If you put this potential into the Hamiltonian for a quantum mechanical model, so basically a vibrational Hamiltonian for quantum mechanical Hamiltonian for our I2 molecule, and you solve it, the energy eigenvalues you get out are given by this. There is a term, a leading term, and notice it's E over hc here that we're talking about, not E itself. There's a leading term which is the harmonic oscillator, absolutely unchanged. But then there's an extra term, and notice that the harmonic oscillator is proportional to the quantum number v plus a half, and the extra term is proportional to the quantum number v plus a half, but squared. And it's got a minus sign. And what that means, what the effect of this extra term is that the levels between the various vibrational states are no longer equally spaced. Down here at the bottom they are equally spaced, but as you start to get higher and higher in energy, basically as you start to approach the bond breaking energy here, right? This is the energy going from here to here is the energy necessary to break the bond. When you start to put enough vibrational energy in so that you're up here at high vibrational states, then the vibrational levels, basically the box gets bigger here, up here. The vibrational levels start to get closer and closer, and so the spacings don't stay equal, and that's accounted for by this term. We're going to see that kind of effect in the data. Going back up here to look at our approximate spectrum, these gaps are not all equal in the actual data, and this is an actually oversimplified spectrum. The real one is a lot more complicated. It's got lots of peaks. Actually, let me just show that so everybody has that in their mind. Yeah, I think here is fine. Here's what the spectrum looks like. And yeah, all these different peaks are for the v equals 0, starting from the v equals 0 level and going up to various different levels on the excited state manifold. And this group in blue here is starting from the v equals 1 level, so v equals 0 is all these guys. That's the red guys here. And then starting from v equals 1 and going up, that's the blue guys here. And then starting from v equals 2 and going up, that's the green guys here. And so you can see it's quite a complicated spectrum, quite a lot of peaks. Also notice the peaks are farther apart out here than they are as you move further and further over to the left. And over here they're getting very close together. That's because this is high enough vibrational levels on the excited state manifold that you're approaching the energy. Let me draw that better. You're approaching the energy where you're starting to break the bond, where you're starting to get close up here to the top. And so they're getting very closely spaced up here. So you see the effects that we're accounting for with the Morse potential in the data itself. And that means, that makes the interpretation of the data a little bit more complicated, but it's also good because it means that we can get out some of these parameters that are connected to the Morse potential itself. And let's see, that is all I want to say for today. Next week we'll talk about the actual nitty-gritty of extracting all those numbers from all those parameters from the data.